Experimental physics has calculated the three gauge couplings to 8 decimal places. The fine structure constant, alpha, sits near 1 over 137. The strong coupling is 0.1179, and the weak coupling is 0.0338. These are treated as pure, dimensionless numbers, empirical inputs that the standard model requires but cannot explain. This gap has persisted for a century. We rely on these exact values to describe how atoms hold together and how stars burn, yet we have no framework that dictates why these specific numbers emerge from the vacuum. Mode identity theory provides a deterministic alternative. It proposes every dimensionless coupling scales from a Planck reference through a single geometric law. In this equation, c theta represents the phase geometry of the interaction, while omega represents the cosmological constant hierarchy, the scale of the vacuum itself. By mapping the topology of the S3 manifold, you can derive the values of all three gauge forces using only structural constraints. This map also identifies a topological boundary condition. This specific geometry prevents the existence of a fourth fundamental force, suggesting why supersymmetry has never been observed. These constants are the resolved fine structure of the vacuum hierarchy. We begin with the S3 manifold and its one-sided Möbius boundary. When a wave function psi traces this edge, it encounters an anti-periodic boundary condition. It requires 2 full laps, or 4 pi radians, to restore its sign. In a manifold governed by the binary icosahedral group, this double lap traverses 120 discrete decisions. This 120-position grid defines the spinorial domain. It is the geographic requirement for half-integer spin fermions, which carry complex pairs. When we shift from the wave function to an observable intensity, we square the amplitude. Mathematically, this operation collapses the 4 pi period into a single lap of 2 pi. This squaring halves the available positions to 60. This is the bosonic domain, the native grid for integer spin particles. Photons are bosons, meaning their coupling strength must be evaluated using this 60-position grid. Because these dimensionless couplings resolve within a single floor of the hierarchy, they move in minimum grid steps of 1 over 60. The connection between spin and statistics is a direct consequence of this underlying manifold geography. Structurally, the electromagnetic interaction is a force mediated between units of charged matter. To find its value, we must locate matter on the icosahedral spectrum. Matter dynamics occupy the 7th Fibonacci well at position 13. Because 13 is coprime to the 60-position grid, it is the point on the spectrum most detached from the geometric symmetry of the manifold. The formula for alpha evaluates this matter well on the bosonic grid, multiplied by 1 grid step of the vacuum hierarchy. The result is 0.00733. Compared to the codata value of 0.00730, the agreement is 0.5%, achieved without adjusting any free parameters. Numerical accuracy alone can be misleading. Without structural justification, a single successful calculation might be a coincidence of large numbers. We tested this by scanning 3,527 mathematical combinations across different grid positions and denominators. While 3 combinations reached 0.5% accuracy by chance, only 1 formula survived the application of our structural constraints, including the bosonic grid and the matter well. The most accurate alternative used a spinorial grid of 120. While the number was close, the physics failed. It assigned a spinorial grid to a bosonic photon. The value of the fine structure constant is the result of these specific topological requirements. This same logic extends to the remaining forces, creating a systemic gauge ladder. The E8 root system, which describes the symmetry of the manifold, has a Coxeter number of 30. This forces exponents to pair according to the depth of the root system. Since electromagnetism uses exponent 13, its conjugate, 30 minus 13, assigns exponent 17 to the nuclear forces. We can map the forces on a matrix of grid assignments. The electromagnetic rung uses a bosonic carrier and a bosonic target. The strong force uses a bosonic carrier, the gluon, to confine spinorial fermions. Evaluating exponent 17 on this mixed grid yields a coupling of 0.1162. The weak force rung involves spinorial carriers, the W and Z bosons, acting on spinorial targets. But the weak force is also the only interaction that fundamentally violates parity. It possesses an intrinsic handedness. This violation traces back to the dodecahedral geometry of the manifold. Each vertex of a dodecahedron has an angular defect of pi/5. Because the S3 manifold features a Z2 Möbius holonomy, a half-turn twist, any interaction traversing the vertex is identified across the gap. This holonomy effectively halves the angular defect to pi/10. This yields a projection factor called the Plato twist, the cosine of pi/10. Applying this to the weak force equation brings the prediction to 0.0339, within 0.4% of the measured value. Parity violation is the vertex geometry of the icosahedron filtered through the Möbius boundary. The gauge ladder contains a vacant rung. This specific slot requires a spinorial carrier acting on a bosonic target. This is the exact configuration required for supersymmetry, where spin 1/2 gauginos mediate forces between scalar squawks and sleptons. However, our topological axioms require that observables are derived by squaring the wave function. This operation is one way. Squaring psi to get intensity is irreversible. It is not possible to reconstruct the specific phase of a spinorial carrier from a bosonic target. The Möbius boundary condition forbids this interaction. The vacancy in the matrix is a structural lockout. This predicts that extensive searches for supersymmetric particles will continue to find null results at all energy scales. The standard model force content is complete because it exhausts the geometrically permitted rungs of the ladder. When we compare the cosmological constant to the fine structure constant, we see they share the same hierarchy, omega. Lambda scales with the full vacuum hierarchy, while alpha scales with 1/60th of it. If we move toward the Planck scale, the effective hierarchy, omega, shrinks toward 1. At this floor, the fractional exponents reach 0. Any value to the power of 0 is 1. The 3-gauge couplings converge as the vacuum hierarchy itself collapses. This means that grand unification is not an imposed symmetry, but the natural result of the vacuum hierarchy reaching its absolute mathematical floor. The fine structure constant is the vacuum hierarchy resolved at its grid limit.